So I'm one of the CUDA architects, which means I spend a whole bunch of my time really thinking about the platform as a whole, up and down the whole stack, how things work together. And so every year I get a chance to stand up here and talk to you all about what it is that we've done with CUDA in the last year, where we're going with CUDA. This talk has been called CUDA New Features and Beyond for many years, because I always think it's important to show not just where we are, but where we're going. And that helps explain why we are building the things that we build. And so, in fact, in this talk, I've got a lot of beyond stuff. There's things that we've done this year. There's things which are coming out this year, which I'll be talking about. And I'm also going to look ahead to the future, because things are changing so incredibly quickly in the accelerated computing space. I mean, you probably all just saw Jensen's keynote. There's just so many things going on that keeping up with this entire platform is the work of hundreds of people. So I am standing here as a messenger because hundreds and hundreds of amazing, brilliant people have worked on all these things I'm going to show you. And so the important thing for me is when you hear me say CUDA, I never mean CUDA C++. Right? My boss saw this, my boss Chris saw this, and he was like, you can't show that. And so, sorry, Chris, I showed it. And I showed it because I do say CUDA C++, right? But CUDA C++ is not this whole story. And when I think of CUDA, when I work on CUDA, the platform that I am one of the designers of, it's all of these many, many different things, right? So in every respect, CUDA is the thing that gets you running on the GPU. Whatever your application is, whether you're working with a PyTorch framework, whether you've got some library that magically does it under the covers, somewhere, somehow, you are intersecting with what CUDA is. Because anything that touches the GPU, by definition, has to go through CUDA, our drivers, our runtimes, the stacks, all of the pieces that work together. Now, when I started at NVIDIA, 2008, so that's, 17 years ago, CUDA was very small. CUDA was just beginning. I was one of the first, there's about a dozen of us. And at that time, CUDA very much was CUDA C++. In fact, it was CUDA C. We didn't even have C++ support at that point. There's a couple of libraries. I was actually hired to work on the FFT library. And so in the beginning, everything that you did, you had to write yourself. But that's not a sustainable way. That's not a platform, right? So CUDA today is much, much, much bigger. This is a set of boxes I could fit on one slide. There's actually, I think, something like 250 SDKs alone that NVIDIA produces. And that will just be the second row from the top there. But there's thousands of things that other people have built on it. Right? I've got DAX and PyTorch on the very top. There's so many other frameworks that others have built that NVIDIA contributes to, we work with, we are involved in every aspect of GPU computing that we can get to. But we have this enormous stack, and we have this enormous stack, because it can't be only CUDA C++, right? If you look at something like PyTorch, which is a big, complicated, seminal AI framework, you've probably all heard of it, right? PyTorch calls cuDNN to do a lot of its work. And cuDNN calls cuTLASS, and cuTLASS has kernels implemented in cuTLASS. And cuTLASS is built on CUDA C++, which is compiled with NVCC and runs on the CUDA runtime, right? All of these things happen when you do something in PyTorch. But PyTorch also calls cuBLAS directly, and cuBLAS has its own kernels, and cuDNN has its own kernels. The point is, right, that all of this works together, and that's what makes this, it's a platform. Nobody sits there and writes every single piece in native C++ kernels, which is why, while CUDA C++ is a core central point of it, it is nothing. I spend less than half my time thinking about it, because it's how all of these things connect together that makes the difference, right? So one of the interesting things here is that as I see the sophistication of software evolve, the technology stack, the software stack, is becoming much, much deeper, right? And so there's another trend which I've seen really accelerate in the last year or two, and it's something that I have to pay a lot of attention to when we think about what we add to these stacks. Right? This is an example of the kind of works that will be involved in any deep learning application, through frameworks, through kernel generators, things like OpenAI's Triton, which is a fantastic kernel generator that OpenAI develops. There's a talk at GTC by Phil Tilley later this week. But one of the things I'm going to highlight for you, I'm going to take the same picture, and I'm going to highlight every layer in the stack that has a compiler. It used to be just libraries calling libraries. It used to be runtimes and things managing data. And now literally every single layer of that stack has compilation built in. That is a real seminal shift. The level of complexity and difficulty of all of these layers has gone way up as a result of this. And so what it also means is that compilation, I've drawn compilation down the bottom of the stack here because you usually think of it as the final thing that takes all of your code and dumps it onto the machine. But actually, you've got these languages, these domain-specific languages, these formal languages, all targeting all these different layers. Every layer now has this compilation in it. And so an interesting question is why? Why are we seeing this transformation? And I think, I hope it's not controversial to say something like this. I think that it's because performance matters, and so optimization matters. And optimization depends on the problem you're solving, right? To give you an idea, if you're an AI expert, you'll be familiar with the idea of a recommender system, which is limited by memory bandwidth, or a graph neural network, which is completely limited by communication. You optimize around communication. Or a language model, which is compute limited, so you optimize around compute. Completely different ways you would optimize these three systems. So if you know you're working on a recommender, you would treat it differently. And this seems like a big universe, but it's actually a tiny corner of the whole universe of all the applications. You can easily imagine that deep learning networks are completely different from scientific simulation, and completely different from graphics and metamaterial stuff, and all the kind of crazy, like procedurally generated stuff that graphics does. Right? So optimization, you need to know something about the problem you're solving to really be able to attack it. And so fundamentally, optimization is a hierarchical problem. And it's hierarchical because you know different things at different layers of the stack. And I think this is why we're seeing the whole depth of the stack, of the abstractions, all producing their own compilation phases. Because if I'm at the very top and I know the whole model, I can start thinking about how do I parallelize my model, how do I distribute it, where do I put my data. I get down to individual operations, and I'm starting to think about how I break these operations down into pieces, all the way to the very bottom where my compiler is doing instruction scheduling, which is completely something that the top level could never be aware of. But each layer has to be able to do different optimizations which suit the different visibility that it has of the problem. And so I had compilers down the bottom here, but that's not true. Compilers are everywhere. And what's one of the interesting things about it, you see code generation everywhere because the way that a compiler treats something is it takes in code. So if I've got a high layer doing some optimizations, transforming something, and then emitting it back out, it has to generate code and emit code back out to the next layer, which is going to take it in and apply its operations all the way down the stack. So you're seeing this inline, just-in-time, data-dependent, problem-dependent optimization and compilation going on everywhere. And so, interestingly, a significant shift in the way these programs run is that compilation, which used to be a big offline build system that you'd run for hours, compilation is now in the critical path. And if compilation is in the critical path, then time for compilation is critical. At NVIDIA, we've spent every year, where I stand up here pretty much every year and tell you about different ways in which the compiler has worked on improving compilation times, because it is important whether you're online or offline. But for JIT compilation, it's especially important. A couple of things the compiler team has done this year is to intentionally give you control over the degree of optimization that these JIT compilations, you can do it offline as well, but these JIT compilations can apply. So if you need an immediate result, because you're just one of a long chain, you can sacrifice for your optimizations, slightly fewer optimizations and speed for a trade-off, for slightly faster compile time. Or you can even iteratively do this. You can start improving over time. And at the same time, something which is extremely normal in offline compilation, which is precompiled headers, caching of existing compilation work, all of those types of things, we have brought them also to JIT compilation. And obviously the difference between having to compile your program or looking it up in the cache and hitting it is infinity, right? You're either compiling or not compiling. So another aspect of this is that you can't build anything without being able to analyze it, debug it, inspect it, profile it, all of those things. And we're used to having these types of tools. I'll show you many of them over the course of this next 45 minutes. But we're used to having these tools for code and debugging of code and profiling of code. Now that compilers are in the fast path, we also need these tools for compilers, right? So compile time tracing, heat maps, telling you where the time is being spent. You can see on the left-hand side lots of processor heading, header processing. which means the precompiled headers would be a big help here. And then on the right-hand side, things like we're building a thing called a compile time advisor, which is similar to what Nsight's tools do, looking at all this data and making a human-readable recommendation for what is wrong and how you can fix it. So really, in a way, the secret of CUDA is that CUDA is not just one thing. This is something Jensen was saying in the keynote just a couple of hours ago, that it's this entire big collection of things that we've built over time to apply to whatever problem that you are trying to solve. And so a big thing that we have done over the last year, over the last couple of years really, is we've been working hard to bring accelerated Python first class into the CUDA stack as well. Right? And because CUDA is not one thing, CUDA Python cannot be just one thing. We cannot just have kernel authoring. We need all of the stack, everything, top to bottom, because you have to be able to write a kernel and drop it into PyTorch, but you also have to be able to call Pythonic libraries and all of these other things, right? So in many ways, you need all of these things to work together just like a normal platform, top to bottom, in Python. Interestingly, you'll see there's nothing in the compiler layer here because Python is all JIT. It's a language built around just-in-time compilation. You don't have makefiles and build systems for Python in the same way. You import a whole bunch of dependencies. And so it's the dependency management which is tricky in Python. It's the thing that I hear a lot from users working with Python. They've got lots of different packages, and keeping the dependencies straight is hard. And so with Python, keeping this interoperability between all the layers is going to be a huge gain for productivity and being able to use Python end-to-end. We've actually got a bunch of talks this year at GTC, specifically curated a track on CUDA and Python. And so I have an index at the end of this talk as well where you can see what's coming on. But just so that you know, if you are interested in native Python programming of the GPU, we have a lot of material walking you through the different stages of how to do this. So I'll summarize for you, though, the kind of things that we've done and the way we're thinking about it, the way we're making these investments. Right? I think fundamentally, to me, Pythonic CUDA is not just C translated into Python syntax. It's got to be something which is natural to a Python developer, that the Python developer's instincts are right. My general principle when designing anything in CUDA is that if you don't really know how it works and you guess, you should be more or less right with that guess. Right? It should not surprise you. And so Pythonic CUDA should not look like C. It should look like Python. So a few years ago, we started out with the initial CUDA Python bindings, which were so things like cuPy could interface with our low-level drivers, one-to-one mappings between Python bindings. But what we have built over the last year, and you can actually go to GitHub and get it right now, is something we call CUDA.core. And CUDA Core is a Pythonic reimagining of the CUDA runtime to be naturally and natively Python. And that means more than just the interfaces, although of course it does mean the interfaces as well. It means that the execution flow and the way that it works is fully in process. Python is built around JIT. You should not be dropping out to command line compilers or anything like that. You should be fully in process, right? And one of the interesting things this does is it reduces significantly the number of dependencies in a Python dependency tree for GPUs. And so this is helping that up and down the stack picture I was showing you a little bit earlier. And of course, there is no software without tools. If you can't detect and identify and analyze what's going on in your code, then there's no use. And so we are investing heavily, and we have been for the last several years, but we continue to add more and more developer tools for Python developers. Profilers, code analyzers, things like the ability to annotate your code and have it show up in compilers with something like NVTX, one of these pictures at the top here, right? And even integrating support for PyTorch, right? Like for PyTorch layer, so you can get the low one of these as a Python trace, just straight out of a PyTorch program. And so, as well as the core base Python, there's also how do I program the GPU in Python? That is the point, right? The point is to take your code, and GPU accelerate your Python code without having to drop out of Python. And we've got a whole range of different things. Well, I'll start at the top here with something called cuNumeric. cuNumeric is a one-to-one drop-in replacement for NumPy. NumPy, the most widely used computational library of any kind in Python, by simply changing an import directive, all your NumPy code goes from running on your CPU to running on a GPU. And not only to running on a GPU, but being able to scale up to thousands of GPUs. So in my little example, I didn't just change the import, I squared the size. And it will project this outwards and run it on 1,000-node clusters. There's a Connect with Experts to talk about these. I keep reference links at the bottom of my slides, so where there are talks which will give you much more information about these, I try and link you to them because I only get 2 minutes to talk about any particular topic, and you can sit down with an expert for 45 minutes and really have a conversation to understand how this works and what it does. Now, a lot of CUDA programming, when you think about CUDA programming in your head, you're not just thinking, I'm going to take Python and magically have it automatically get GPU accelerated. That's a very cool thing to do. But if you actually want to craft your own code and invoke parallel CUDA code, the most common way to get to CUDA for all of time has been through libraries. Like, honestly, 90% of all the code that you ever need to write, someone at NVIDIA, some ninja, has already tuned parallel library functions to do an amazing job. And you would be crazy to write your own library function. Nobody writes a Fourier transform these days. There's people who spent years perfecting the Fourier transform. Just use that, right? So the value of libraries is enormous. And so we've taken the library set and we've put them into a package called NVMath Python, right? NVMath Python, it means, of course, Pythonic library interfaces, but it's also unified interfaces. It contains both host-side interfaces to call the libraries from your normal CPU code, and device-side interfaces, so you can plug these accelerated algorithms directly into Python kernels you're writing, which I'll tell you about in a moment. Right? It also invokes or leans heavily into JIT compilation as well, in that the performance, the ability of a library to work efficiently if it knows what your data types are, your data sizes are, and so on, to be able to fuse library calls together is an enormous improvement in performance, a huge difference. And so because Python is such a JIT native, a just-in-time compilation native language, we have built the Python math libraries to take advantage of that. And so you just naturally, just-in-time compile these things just through the APIs that you use with the libraries. And then finally, these libraries, it's not just GPU libraries. Python runs across all sorts of different systems. So that same library package can steer to CPU execution, either through the NVIDIA performance libraries for ARM or through interface to the Intel MKL libraries for x86. It interoperates in terms of array types and so on with lots of existing tensor libraries. And importantly, you also plug in to the multi-GPU scaling that our libraries natively have. And all of this just comes under one heading, with the Python wrapper able to decide and help you dispatch what you want where you want. And it's been very successful already, right? This is a slide that has a pretty picture, so I like showing pretty pictures. But it also has a great little example of some scientists, some researchers at Duke University and some other establishments who took a supernova analysis program for a space telescope that will be launching in a few years' time. They first accelerated it with cuPy, and then they added in these NVMath accelerated libraries. This was not us helping them. This was them taking something, scientists who write Python, who write NumPy, taking this Pythonic interface and being able to drop it in directly. And then, of course, for the 10% of the time, or the 1% of the time, the library doesn't have the function you need, or when you need to glue your library pieces together, we've got a couple of different places. We've got something called CUDA.parallel, which equates, if you're familiar with C++, to the thrust libraries in C++. These are fundamental parallel algorithms, which, again, you just call straight from your CPU, like sorting or histogramming and things like that. And these are accelerated libraries of these algorithms that you will combine into making your parallel algorithms. Or we have CUDA.cooperative, which is when you're writing your Python kernels. And yes, I will get to that, don't worry. When you're writing your Python GPU kernels, you can still tap into these extremely high-performance, ninja-tuned accelerated libraries. No one in their right mind should ever write a sort, just like you shouldn't be writing an FFT. You should be depending on someone who really knows a lot about this to have written it and perfectly tuned it for the GPU. And because this sits on top of the underlying infrastructure that we've built over the years, that enormous stack of stuff that I showed you right at the beginning, we didn't re-implement these in Python. We made sure that it links in the underlying fine-tune C++ code, so your performance difference is negligible between Python and C++. You are not sacrificing anything. It is a critical requirement of CUDA that we should give you access to all the performance of the GPU. You're going to the trouble of using a GPU because you want to go fast. We have to give you the ability to do that. You've got the productivity of Python combined with the ability just to tap in to the same performance that you would get as if you were in C++. And so finally to the kernel authoring I've been promising you. And before we get to the kernel authoring specifically, I'm going to refresh you or tell you a little bit about how running kernels on the GPU actually works. Many of you who are familiar with CUDA will already know this story, but I think I'm going to take it to a few places you haven't seen before. In general, what you do with a GPU kernel, you start with an array of data, right? You've got some bulk thing that you need to process. You're not going to use the GPU just to calculate one sum. And very often, that's all you do. You take your bulk array of data, you write a kernel in PyTorch or in NVIDIA's Warp, which I'll talk about later as well, or one of many other different things. And that system, that compilation system, will then take it and map it to the GPU for you. And a lot of the time, that is just what you need. It accelerates you, and you're great. And so a lot of people, you should never do more work than you need to. If you can do it in one line instead of in 100 lines, do it in one line. Right? We're all programmers. We're fundamentally lazy. And so grid-level parallelism is really an easy way of accelerating you. But it's not it doesn't get you all the way there. Right? You can get a lot more performance, sometimes with just a bit more effort. And so the way that CUDA breaks things down is you take your program and you break it into separate pieces. This is true for multi-core or multi-node development as well. You need to find independent pieces of work that can be worked on in parallel. And then for CUDA, what you do is you launch what we call a grid of blocks onto the GPU to process these tiles of data that I've broken my problem into. And then for each tile, one block will process one or often more tiles than one. Inside that block, I have up to 1,000 threads. And each thread will pick a data element and work on it. And we get parallelism in CUDA on the GPU by ganging these threads together. Each thread is doing a single element operation. And by ganging them together, we get bulk parallelism. And in many ways, this is the superpower of the GPU. I think really, to my mind, this is the main differentiator about why GPU computing scaled in a way that we didn't see for the sort of the SIMD vector-based CPU computing. Is because you have this SIMT, as we call it, single-threaded execution model, where if you gang them together, you get bulk parallelism, but you don't have to. You can still control fine-grained parallelism. That flexibility has allowed the GPU to apply to an enormously wide range of different applications. But we don't necessarily have to go all the way to thread-level parallelism. Right? I've gone from the big array of data to the fine-grained array of threads, but we can stop halfway through. We can stop at the first step. If I divide into tiles, and then just take my tiles, it turns out that very often my problems, my applications, my tiles are not random scattered data. They're structured. They're vectors. They're tensors. They're arrays of some kind. And so I can apply whole array operations automatically by taking a block of these threads and just telling the compiler, do it for me. You figure out the thread mapping. So my problem becomes easier. I'm only doing step one. I'm not doing step two. And in fact, very often the compiler will do better than I can do, because the compiler deeply understands all the fine details of how the GPU runs. And so what we have is we have these three different levels of parallelism. And all three, right? Remember, CUDA is about having a menu of all these different options. There is no one size fits all. There is no one layer to rule them all. Right? And so we have the grid level models on the left. We have the traditional thread level SIMT stuff on the right. But I really want to talk about this middle thing, these block level models, because I think that has a really nice balance between the effort and the reward. So we've built a thing which we call cuTile, which is tile programming for CUDA. It is an extension for CUDA. And instead of operating element-wise, like at the bottom of this picture, what we have instead is array plus array equals another array. And because these arrays are structured, the compiler can do a great job of mapping these efficiently onto the GPU. So your problem just became much easier to think about, much easier to debug, much easier to state, and very often, as I said, much more performant. There's a lot of these things out there. OpenAI's Triton would be a good example, right? And I think that those are a natural fit for Python programmers. The other obvious thing about an array or tensor-based models, it maps to things like tensor cores. There's a lot of parallel hardware engines inside the GPU, and the ability now to express your problem of here are the tensors, lets the compiler say, well, I know what to do with these. I know how to put these things straight on the GPU. And so we can map these things to tensor cores, and because cuTile is built into CUDA, it is a fundamental extension of CUDA, all of the CUDA portability and generational guarantees can apply. And so suddenly your program, expressed as tensors, can run on any architectures, no matter what happens to the hardware layers under the covers. And so cuTile is built into the CUDA platform stack. If you've been sharp-eyed, you've noticed it's actually been there in my picture all along, and I haven't told you about it until just now. But it's very important to understand that this is not just another library. What we've done is we've embedded it as part of the CUDA language and as part of the CUDA platform, which means it runs everywhere CUDA runs. Right? It has all the stability and portability guarantees. It runs on Windows. It runs on Linux. It combines and interfaces with CUDA graphs and all the other things. We've got debugger tools and all these other pieces which support it. It is just a piece of CUDA, but it is a way to express your problem, not necessarily at the thread level. If you can get away with something at the tensor level, at the tile level, then you tile your problem, and cuTile is the target that you're going to want. And so I think really, my colleague Mark Harris, who's been at NVIDIA longer than me, he's been bugging me for 15 years or something to make simplified CUDA. So Mark, we finally did it. We finally given you a way to simplify CUDA and still keep the performance that you would get with thread-level parallelism. Right? It simplifies an enormous range of applications, I think. Where obviously, this is something we build, and we build it over time. And so while initially the first release of this, which will come out a little later this year, can support mixing and matching tile kernels and thread kernels in, say, a CUDA graph or something like that. The goal is to be able to make these things interoperate even inside a single kernel. So that, because some problems are well suited to tiles and regular arrays, others, like compression or hash tables, are suited to threads. And so you should mix and match and use the right tool for the job, even within a single kernel granularity. And so that is where we're going with this thing. But I think, to come back to what I was previously talking about, it's fundamentally more Pythonic. Right? Python programmers today don't think in threads. They think in terms of arrays. NumPy is array plus array equals another array. So I've got a NumPy example on the left-hand side here. And cuTile is tile-based. It's a blockwise model. You explode your data into pieces, because it's not right, and because you know better how to break your data up column-wise, row-wise, square, rectangle. You know your problem. Remember, optimization is a domain-specific problem. You know the problem you're trying to solve. But syntactically, you're still performing array operations. I think it's fundamentally much more intuitive. And so it's not, while the first thing that we're going to put out is a Python interface to it, we will also, because this is a core part of CUDA, we will have a C++ extension as well to be able to do tile programming. And you can see, this is still syntax that we're developing. But you can see that these things look very similar. On the left-hand side, I have one of numbers examples off the internet, which is a matrix multiply in thread level code with shared memory and other pieces, and threads and other pieces like that. I think the code on the right is much more accessible, much easier to read, much easier to understand what's going on. And fundamentally, it comes out to the same performance. So what we did with this is we took cuTile and we implemented a Llama 3.1 inference. And so we ran this out of PyTorch because nobody wants to write their own KV cache. But but in the same way that you can take hand-rolled kernels and inject them into PyTorch, we ran this thing through PyTorch. On this chart, I've got, as an example, the standard Torch Eager backend, which runs, I've compared everything to cuDNN. The Torch Eager backend runs about half the speed. But cuTile gets actually shockingly close to a cuDNN backend for PyTorch. Right? And cuDNN is, of course, written in C++, but more importantly, it's been, it's hand-tuned over many, many years. And we took this, and in the matter of a couple of weeks, we put this thing together and ran a Llama inference that's within 10% of hand-tuned cuDNN, completely in Python, with what actually is a brand new compiler. And compiler optimizations are things you add progressively over time. So that was very exciting, but we didn't want to stop there, because it's not just a tool for making AI networks. CUDA is a tool for doing everything. And so We also ported one of the standard HPC mini apps, they're called. It does a 2D fluid simulation, and we wrote this in cuTile as well, because we wanted to be sure that we're building something that is general. So we've got different types of fluid mechanics going on here, Llama inference going on, and the previous slides as I showed you. We have a lot of, the goal is that this works everywhere that CUDA works. And so to be working everywhere that CUDA works, again, there is no software development without tools. And so the developer tools also apply to the tile, to cuTile, to tile programming. Right? This is actually a set of Nsight Compute and Nsight Systems traces from the Llama 3 run that I was showing you before, the one that came within 10% of cuDNN's performance. Right? And as I was talking about earlier, there's compiler stacks up and down the whole abstraction layer. Everywhere needs compilers. And so we know when we build something, we're not just targeting humans writing code, or at this point, AI code assistants also writing code. We're also targeting compilers writing this code. And so while cuTile is the name of the language extension, which allows you to do tile programming in CUDA, we've actually built two different layers here. A higher level layer in Python and C++, and then a lower level layer, which is really a compiler target, which aligns with sort of the thread path of NVVM and PTX. So now, in the same way that PTX is for parallel thread execution, TileIR is for tile-based execution and all the optimizations that go around that. And so you can have compositionally tile code and thread code working at the same time in your workflow, running through these different compiler optimization phases and coming out together into a single underlying GPU executable. And this GPU executable can be on disk, which you can distribute, you can JIT it to future architectures, or it can, of course, be at runtime code generated. So now, finally, having told you about how the GPU runs code, I can tell you more about native kernel authoring in Python. Right? And just like we have many ways to accelerate applications, we have many ways to program kernels. Right? There is no one-size-fits-all. And so really fundamentally important to the ability to write any complex big application, in this case an example of physics, of molecular biology simulation combined with AI, you are going to use many, many components together, to compose them together to make your program work. And so always forefront in our minds is not just what does this one piece do, it's how does it do it with relation to all the other pieces. How do I make sure that I can run my Llama 3 model in PyTorch with dropping in some kernels from cuTile and then sending it through the auto-differentiating warp simulation. Right? All of these things working together is much, much more powerful than trying to figure out how to connect them together separately yourself. So an example, I talked about the NVMath libraries earlier. And the NVMath libraries not only have host APIs, they have device APIs. I thought there was a really interesting example of composing different types of programming model, attacking it two different ways of integrating these Ninja accelerated libraries into code. Right? Number CUDA is a low-level, thread-level Python way of writing kernels. It's been around for quite some time. And you can call the APIs directly from there. Warp, on the other hand, is an auto-differentiating framework built for combining AI and simulation. And so they expose them very differently, but because, again, they go through these lightweight interfaces to get to the underlying core C++ performance, the performance is identical from native Python code, no matter whether you're in C++, Python, using number CUDA or warp. And I want to talk about warp a little bit more because they actually did something really interesting this year. I talked about them last year. I think I maybe even showed those same pictures. Warp is fundamentally a grid-level kernel programming domain-specific language. It's a framework, really, for building simulations. And it has auto-differentiation, so it can naturally generate backwards passes and train AIs through these physics simulations that you have built. In the last year, Warp also has said, we need more than just a grid-level model. We need a tile model as well. And we need a tile model so that people can more tightly integrate neural network layers into Warp. They can fuse kernels. They can do all the things that I said earlier, grid-level programming is easy, but there's a lot there on the table if you just add a few more pieces of parallelism. And they've really exploited this in some very impressive ways. And so, as well as native kernel programming, there's even native Python tile-based programming we can talk about now, right? My core message in this whole talk has been that one size does not fit all, right? The platform has countless different options because it has to serve all the different applications. And so there's no one tool. You're going to pick the right tool for your job, right? You're going to pick the option that matches what you want to do, simulation, or LLM generation, or pure raw tile programming for some of those HPC things I was showing you. And cuTLASS in the bottom here is actually something I want to talk about a bit more. cuTLASS is, if you're familiar with it already, it is the way that you program tensor cores. It gives you full control, full authority over every bell, whistle, and knob. You can get the maximum out of the tensor cores of the GPU with cuTLASS. And cuTLASS has implemented a Python compilation layer as well. So that, again, native Pythonic programming. It's not just C++ looking like Python. This is full native Python, right? And it matches, through some magic that I don't have any idea how they pulled it off, it matches the performance of and the code generation of the C++ cuTLASS from Python cuTLASS. cuTLASS 4.0 just combines the two of them, right? The productivity of Python with all the performance that you're not sacrificing in any way at all. But because you're in Python, you're not paying the price at JIT time of C++ template compilation, which is very expensive. There's a talk on this by several of my colleagues later this week where they go into depth about exactly what the Python interface looks like, and they will discuss some of the JIT compilation as well. But simply going straight from Python down to these low-level IR layers, right? That is so much faster just in terms of iterating and auto-tuning and so on compared to doing it in C++. I really think that we would see most users of cuTLASS being interested to say, well, does Python make sense or does C++? Now you have these choices and you have these trade-offs that you can make. And so I've talked about, this is really the last section because I've only got a few minutes left. I've talked about the CUDA platform stack, right, for all of this talk. And I've showed you this set of layers, but really we've been talking about programming a GPU. How do I get my program on one GPU? And the reality is, nobody runs on one GPU anymore, right? You all saw the keynote where Jensen's showing giant data centers of things. I think Jensen's actually right about giant data centers. It's not just those things. More and more people are going to be running one of these. A few weeks ago, I was talking to someone I know from one of the DOE labs, and I was telling him about the Python work we've been doing because in HPC applications, Python is also becoming not completely predominant, but it's definitely growing significantly in HPC. And he turned to me and he said, okay, that's great, but what are you going to be doing 2 years from now? And I thought that was an interesting question. I said, well, what I'm going to be doing 2 years from now is because the future is this massive data center scale computing, I'm going to be working on multi-node CUDA. And I thought I'd tell you a little bit about it. And this is just our early thinking on it. What are the things that we need to think about if we are going to be talking about a runtime system that scales to the whole data center? Right? There are whole different sets of problems that you have when you're on 100,000 nodes and when you're on one. Right? And so we call this thing CUDA DTX, and it is intentionally going to be CUDA built to span the data center and scale. And so the important things for this, in my opinion, when I think about CUDA, this is a picture really of how I think about CUDA. I think of CUDA as being this interesting confluence point where you've got all these accelerated applications up the top and all this hardware down the bottom that we pretend really hard to you is all the same hardware, but it's not. And so we've got to somehow connect applications to disparate hardware. And you do this, and this is going to get a little bit programming model-y for a moment, you do this with two key constructs. One is something called a machine model, which is to say for all this different hardware that we have, GeForces and mobile chips and data center things and Hoppers and Blackwells and Amperes, all of those things. All of those have to be presented to you so that they look and feel the same. Otherwise, you'd go crazy. You'd have to write your application 6 different times for 6 different platforms, right? So CUDA's job is to unify what the machine does without compromising the performance that you can get out of it. We do this in tight cooperation with the hardware designers as well, of course. We're in this very fortunate position that we make both the programming language and the hardware that runs it. So we negotiate what we put in CUDA and what we put in the hardware. But this machine model is fundamental to being able to treat the GPU as a GPU instead of lots of different pieces of hardware. Along with it is a unified runtime. That is to say, the instructions, the APIs that you call to launch work and create CUDA streams and all those things, they all have to be the same. If I had to allocate memory differently on different hardware, you'd go crazy. It's exactly the same kind of problem, but from a programming API perspective. So these two pieces, this is the U in CUDA. CUDA is now a proper noun. I think I'm the first person to have actually expanded the acronym onto a slide in a long time. But this is the unified part of CUDA. This is to bring together these core pieces of what programming this hardware means. And so when I think about distributed CUDA, I think we need to think of a distributed machine model and a distributed runtime. And what are the properties of those? And this, I'm literally telling you about something 2 years from now. I have no idea what the final thing looks like. But I just thought I would, this is CUDA and beyond. This is the beyond part, right? Where I'm going to be, where I tell you, here's what I think, if I have a distributed machine, I need naming for resources. But topology really matters. What's next to each other matters. It's got to be resilient. If I've got a 100,000 node machine, things are going to go down all the time. Something that happens one time in a billion over 100,000 nodes, it happens every day, right? And at the same time on the runtime, what works well at scale is not necessarily what works well on a single GPU. It's got to be asynchronous. The scheduling has to be dynamic. It has to be controllable. These are the kinds of things that we are thinking about as we say, okay, let's feel around. I'm not telling you of any product that you can use or anything. I'm just pointing at the direction of what we believe will run efficiently on the GPU machines of the future. Now, there are things we are doing now for distributed computing. And one of the things which I've told you about, if you've come to this talk over the years, for the last several years, is data center scale distributed tooling. And so the Nsight systems tools have a thing they call Nsight Cloud this year. There's a colleague of mine who's giving a talk about this and many other things linked at the bottom there. Data center scale debugging. But what they're doing with Nsight Cloud is dropping pieces into containers so you no longer have to run special debug containers to go and get analytics out of your code, right? Another thing that we've been doing in CUDA is building system tools, system scale tools for managing this, right? And we built something called CUDA Checkpoint. It's based on a Linux utility called CREU. And the key piece is you don't have to instrument your code. It can reach in, interrupt your code, snapshot it down into some memory, save it on disk, and restore it later. This is what checkpointing does, and this is what CREU has been great for Linux CPU programs. We've extended it to be able to cope with GPU programs as well. So now you can snapshot it and pause it and then unpause it later. And one of the really interesting things you can do with this is you can migrate your data. It means I can snapshot it off one machine, and as long as another machine is still running the same GPU, I can rematerialize it on another GPU. I can do load balancing across my data center. I can group things onto half-empty machines. I can do all sorts of interesting things now that I can migrate code. The system administration can migrate code without the code ever being aware of it at all. It's these types of things that are going to enable this at-scale execution. And this is my last slide. But what we've done this year, I am truly just the messenger. There are a ton of amazing engineers and people behind me who are producing all this incredible stuff. I just stand up here and get to talk to you with some pretty pictures. We've curated specifically a set of developer sessions at this GTC listed here. There's a QR code where you can jump to a landing page and see it, which covers this whole breadth of all the things that CUDA is able to do. And of course, my final slide is always the list of talks that I have referenced here, if you want to find out more about the things which I have said as well. And that's it. Thank you very much.